Attention to is something called the section break. And the section break allows you to have one type of formatting in this section, a different formatting here, and then again a different formatting here. So those are very useful tools to change things back and forth, okay? And I could use it. Some people don't like this thing because if you have like 5 spaces, you're gonna see 5 dots. Like if I put dog, space, 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 you see 5 dots there. But when you print, this stuff is invisible. It's just ultimately every character has a computer code, and this mode shows every single character in every single document, including the blank spaces, the breaks, and things of that sort. Okay? So if you have problems formatting things, use this tool. It can show you why what's in there is invisible is messing things up. Questions? So ultimately, if you're presenting a report to somebody, you're either building a PowerPoint or you're creating a Word document that somebody's just gonna read. And you are the technical person with the quantitative skills. You have to translate that to non-technical words or whoever's gonna read it. So even though this appears to be something stupid, it's not. It's actually something that is, if you're struggling, definitely you need to know it. You need to learn it before you get a job. Questions? We good? All right, so what did we do last time? We figured out the ideal portfolio for the investor, right? So we said, if you invest in risk-free MP, then you can mix those 2 assets together, and you can figure out the risk with a combined portfolio like this. You can figure out the expected return of the combined portfolio as Y, ERP plus 1 minus Y, RF. And then we mix those 2 together to assign the best possible portfolio for the investor by measuring the utility. The utility was given by ER, expected return on the asset minus 1/2 A sigma squared, right? And then we said, if you were to measure all the different levels of utility that you can possibly get by investing in those 2 assets, you will find out that there is one blend, which we call Y star, which produces the highest utility for the investor. And how do we find it? We say, well, numerically, if you know how to calculate the risk and the expected return of the combined portfolio, all you need to do is just mix them in different blends, whatever levels of risk and return that you get, plug it in here, and then trace the utility, and eventually you're gonna find the point that is the highest. But then we use an analytical solution, and we figure out that that will equal to ERP minus divided by A sigma P squared. Is that right? Mm-hmm. So this is a way to directly figure out the best possible blend for the investor. Then we mess with this a little bit, and we say, well, let's see if this makes sense. If somebody has a very high level of risk intolerance, so that person doesn't like risk a lot, the value of A is going to be very large. that means that you're dividing this quantity by something that is very large, so y is gonna be close to zero. Makes sense. Y close to zero means the investor is taking low risk, and of course he's paying a price for it because he's also exposed to low returns. So somebody who has a high risk aversion would want to invest in T-bills more than the asset. So this formula is consistent with reality. The lower the value of A, the higher the value of Y star. So the investor is willing to take more risk for capturing higher returns. So that's where we stop, right? Yeah. So today we need to mess with this a little bit more, and then we'll change scenario. So today I want to cover shorting. So this is gonna be part of your second project, by the way. So pay attention to it. So far, if shorting is not allowed, we said Y was bounded between 0 and 1. So only long positions allowed. Yeah, so that's what the stuff we have done up to this point. Well, what if you can invest more than 100% in P? How is that possible? But the only way for that to happen is if you borrow money from someone else. So should this happen, if you want to accomplish that, that means that you must borrow. Okay. So that means that the weight for P can be greater than 1, but since the sum of the weights must equal 0, it follows that the weight of the other asset must be less than 1, less than 0. Otherwise, the weights wouldn't add up to. Sorry, some of the weights must be 1, not 2. Wrong class. Yeah. So if I can invest $110, but I only have $100 to invest, that means I must have borrowed $10 from someone else. So, what would be the implication of this? So let's suppose you can only invest in P and F. Okay. So those are the expected returns, the combined portfolio, and this is Y. So how do we compute the expected return of the portfolio? The ERC is equal to, we have the formula right there, which written the way we did it last time is equal to this if you rewrite it. So if you have those numbers, and if I remember from last time, this is the slope, this is the y-intercept. So it's the same equation as last time. If you pick y values of 0 and y of 1, if y is 0, that means you're investing in a risk-free asset. If y is 1, you're investing in P. So at the extremes, you have What if y is bigger than 1? Well, you're still dealing with the same line. But now perhaps you're somewhere around here. Say 1.3. So your opportunity set is now the same line as before, but stretched a little bit outward, okay? Yeah? Does it make sense so far? What do you think is gonna happen to risk?
Risk is also important.
So for risk is the same thing, so I'm gonna draw it here, for risk. So the graph here will be the graph for risk, of course a different scale, but same x-axis. If y is 0, then sigma p is 0. You start from here. You're only investing in the risk-free asset, therefore you have no risk. If y is 1, then sigma c, the combined portfolio, is equal to 0, sigma c is equal to sigma p here. So you're only investing in p. So if y is greater than 1, then you have the same line passing through the origin, except extended outwards. Okay. So essentially you can achieve a higher level of risk by shorting T-bills and investing in asset B. Yeah? So let's apply it and see if this makes sense. Example. You can invest in P, which has an expected return of 10%, a risk of 15%, and T-bills, which have a return of 1%. The question is, how could I achieve an expected return of C of 13%? If my coefficient of risk aversion is 2, is such a portfolio optimal? Okay, so you can invest in an asset, a risky asset with a return of 10% and a risk of 15. And you can invest in T-bills with a return of 1%. How can I achieve an expected return of 13% overall? So let's graph it. So if you invest all in T-bills, this number is a 1. If you invest only in the risky asset P, the expected return is 10%. So how could you get the return of 13? Well, 13 is up here. So the only way for that to happen is if the investor is allowed to short and invest this much in asset Y. So let's figure out what Y is. We want the expected return of C is using that formula there, is the risk-free. That's Y. We have P minus RF. And we know what our target is. Our target is 13%. So we know these, we know everything else. Find Y. So subtract that F from both sides and then divide by these. Or alternatively, you can just use numbers. Your choice. Yeah. So let's find the weight that generates a portfolio with a return of 13%. So 13% goes here. Risk-free is 1. This is 10 and 1. So you get 12 divided by 9. Yeah, it's 1.3 repeating. Is that right?
Yes.
So what does it mean?
That's how much you need to achieve that expected return.
So if I had an endowment of $100 to start with, in order to get a return of 13%, I need to invest 133. How can I get 133 if I only have 100? I need to borrow the remaining $33 by shorting T-bills. Yeah? Questions? So this is 1, this is 1.33. Repeating. The implication is that investor has the following weight. $1.333 in P, and remember 1 minus Y is the weight of T-bills. That's to short T-bills. Questions? So let's say for part 2, if my coefficient of risk aversion is 2, is this portfolio optimal? So there are different ways to go about it. And one would be, well, let's find what is the optimal asset allocation. The optimal asset allocation is what is the EIP minus RF A sigma P squared. So the expected return of P is 0.1, 0.01 times 0.15 squared. So what do you get?
The answer you get is 2.
You get a 2?
Yeah.
Do you agree with that? 0.09 divided by 0.15 squared. Then divided by 2.
0.045.
Yeah, should be right. Yeah. So what does it mean?
Means for the optimal portfolio to achieve maximum satisfaction, you need a weight of 2 in the risky asset.
So what would be a weight of 2 for this thing? the weight of two will be even farther out, somewhere around here. Yeah, so what is the conclusion here? Since your weight of 1.3333 is less than your y star, which is 2. This means your portfolio is too conservative. Yeah. So this investor is willing to take even more risk than that. So it's suboptimal. How do you get? How would you construct a portfolio with a weight of 2?
Well, you'd have to, short on the, presumably try to,
So how many T-bills would you short?
100%.
So if you have $100 to start with, this is telling you that you need to invest $200 in P to create this optimal portfolio, which makes you what, $100 short?
Yeah.
So you need to short T-bills for $100. Okay. So you have your $100 to start with, you're borrowing the remaining 100, and now you have $200 available to invest. Yeah? Questions? So can you handle a problem like this? So let's change things around a little bit. What if now the investor, you can invest in B, T-bills, or you can borrow at some other rate. Let's call it RB. How would things change? And let's suppose that this RB is greater than the risk-free rate. So how would the opportunity set look like? How would the graph change into? Well, I cannot short T-bills, I can only borrow at some other rate. So the moment I'm borrowing, the rate is different than the T-bill rate, is actually higher. So what this leads to is this. These are the expected returns. So in this scenario, if y is between 0 and 1, I'm investing in P and RF. The moment I start borrowing, so this is two long positions, but past this point, long in P and borrow. But the moment I'm borrowing at P. So if this is the risk-free rate, and this is the borrowing rate, when I'm on this part right here, my portfolio is no longer composed on T-bills and P, but here my portfolio is composed of RB, the loan, and P. Does it make sense? So, how do you compute the weight? How do you compute the actual expected return? Well, it's the weighted average of the returns of the assets. So you have, what assets am I using here? The loan and P. So the formula is the same, except the assets I'm mixing together, they're different in this stage. So how would this graph look like? It's the equation of a line right? Even though this is all only true for y greater than 1, then the continuation of this line still exists here, but then only applies from this point on. So you see there is a kink, and this is occurring because you're borrowing at a rate greater than the TB rate. So this is broken here. Yeah? Questions? Yes, no? If I give it wrong like this, can you handle it? You tell me, I know how to do it. Can you do it? And if you have a question, where is that? It's confusing.
Huh?
Sounds like you have a question.
No.
Do you have a question?
No.
Nobody wants to ask the question. I don't want to be guilty of
Well,
asking
you
the
look
question.
confused, so.
No, I'm just trying to see what he's saying.
I'm not saying anything, I'm just standing here, taking a break.
So I suppose the question would be.
It was exhausting already, so I need to rest now.
Yeah.
Oh, I said I suppose the question would be, I'm assuming you would put RB in for RF's place over there if you're having to solve the optimal utility.
So
I don't think he would.
you're ahead now.
Oh,
Just,
okay.
just take a
I was
second.
just thinking that, just replace.
So
Could you,
let's start with an application then, and then we'll see. So examine question number 4. Consider the following. You can invest in P, which has an expected return of 12% and a risk of 20. The risk-free asset, which has expected return. Sorry, it's just a rate, 2%, but you can borrow at 5%. Okay, so those are the possibilities. And the question is, what weight would produce an expected return of C of 8%. And what weights would produce an expected return of C of 14%. Okay. So I would start with a graph just to figure out what's going on here. And so let's see, if I invest only in T-bills, my return will be 2%. If I invest only in asset P, my return would be 12%. Do you agree with that? So for the first question, it says, what weights will produce a return of 8? Well, if I mix y between 0 and 1, how do I get to 8? Well, 8 is where? Here? So in order for me to get 8%, I would have to invest in what? A combination of T-bills
And the receipts.
and the risk-free asset. So let's figure out what the weights are. So to get a return of 8%, mix B and F. So the expected return of C is equal to the risk-free asset plus Y. Here P minus RF. So using those two assets, find Y. You get that? So you're expecting an answer to be between 0 and 1, right? So let's see if the math works out. So here see that we want, the target is 8%. The risk-free is 2. The risky asset is 12. So 0.6. Yeah. So what does it mean? You have to invest what?
60% in the risky assets.
60% in P. And the remaining 40% in T-bills. Yep. What about 14%? How can I get a return of 14%? 14% is up here. So with investing in that asset P alone, I will not be able to do it. I will have to borrow money. So anything above here means you have to, somehow you have to borrow. And the moment you're borrowing, you cannot invest in T-bills anymore, but you have to invest in that loan. So to get an expected return that is greater than the expected return of P, you must borrow. So your portfolio basically is composed of P and the loan. So those are the two assets you're mixing together. And so you would have here C is equal to, how do we call that? The loan, let's call it RB, the borrowing rate plus Y, here P minus RB. So the algebra gives you that Y is equal to here C minus the borrowing rate divided by here P minus the borrowing rate. So put the values in there. C is 12. Sorry, not the target, is 14. The borrowing rate is 5. P is 12. So you get 9 over 7. What do you get?
1.28 roughly.
1.28. Yep. So if you want to invest, if you had a wealth of $100, you need to invest 128 in P, which means you have to borrow $28 at that rate. Yep. Questions? So if you were to graph this thing, this is what a plot half. This is a plot half. So a quarter is about this much. So a quarter, 1.28, would be somewhere around here. And to go from 12 to 14, this is too high, but if I actually drew this to scale, you would see that this segment of the line is lower than the other one. Yeah? Questions?
So in like a realistic scenario, usually the borrowing cost probably would start to increase the more you try to borrow, right? So would it actually start doing like a
So
down-
possibly, I mean, if you have, yes, it could be that if you borrow up to a certain amount, it's gonna be this much. If you borrow more, it's gonna be higher. So possibly it could be a bunch of segments. Yeah, then like that. Yeah.
So we're using the symbol RRB for the borrowed instead of originally it was RB.
Yeah, so essentially you are replacing RF with RB
Yeah.
in the same formula.
I was just saying because you had RB on that one and then RRB on this one.
Yeah, sorry, I don't know why I switched it. Yeah. Rate of borrowing.
Yeah.
Yeah.
I mean,
Yeah, sorry. Questions? So in the next project, you will essentially have to build a portfolio for an investor. You will have data about a risky portfolio, you will have data about, I'll give you data about T-bills, and I want you to figure out, given a level of utility, of risk aversion, what is the ideal plan for an investor? And then I want you to figure out in Excel, I want you to graph utility as a function of weight. I want you to show me that what happens when if you were to change A. So if you change the coefficient of risk aversion, what happens to that graph? So all you need to do, if you write a formula in Excel, you can modify the value of A and see that this graph is gonna shift to the left, to the right, and up and down. Okay, so I want you to actually get a feeling for what would be the ideal portfolios for different investors with different preferences. Somebody who's more risk averse is gonna prefer something that is less risky. Somebody who's more risk tolerant is gonna prefer something that is more risky, but is rewarded with higher returns. Okay? Questions? You good? You ready for new stuff? Yeah. All right. So far we figured out what was the ideal asset allocation for somebody who can invest in either a risky portfolio or T-bills. Let's change scenario and let's see what is the feasible set. For two risky assets. So we don't have a risk-free asset and a risk-free, we just have two risky assets. We're gonna call them, I forgot what your group uses, I think E and D, meaning equity. And debt. Think of it as bonds, okay? So typically, what would you expect equity to do in terms of these returns compared to bonds?
You'd have a higher risk.
Equity is more risky and probably is gonna have higher expected return. So we're gonna say that the expected return of equity is higher than the expected return of debt. But also the risk of equity is gonna be greater than the risk of debt. Okay. Yeah. So if you were to plot those two things in a graph, risk and expected returns, you will plot here and you will plot here. Yeah. Why is D not on the y-axis?
Still risk.
It still has some risk, right? So maybe if you want to be accurate, just say that this is bigger than that, but both of them are bigger than 0. All of them have some risk. Yeah. Questions? So we also need to add more details here. We're gonna say that this is the weight of equity. And this is gonna be the weight of debt of bonds. And of course, the sum of the weights is 1, okay? So the implication of it is that in many cases, if you're solving for weight, you want to write one weight as a function of the other. So it will be useful to write, for example, the weight of debt is equal to 1 minus the weight of equity. And you're gonna see why that is gonna be useful in a second. Questions? You mind closing the door? I'm having a good time too, but. Thanks. So let's see what happens to the relationship between expected return of a risky portfolio. Let's call it P as a function of the weight of equity and implicitly the weight of debt. As long as you know one, you know the weight of the other, right? So remember, the expected return of a portfolio in general is the weighted average of the returns of the assets that you have in the portfolio. So we're going to apply this to this scenario. We have the expected return of P is equal to the weight of equity, expected return of equity, plus the weight of debt, expected return of debt. Alternatively, you can write this as WERE. We can write this as 1 minus WE, here D, which sums out to be this. So distribute this guy over. And that, and I don't know why this became a P, this is a D. So factor out similar terms. Yep. So, let's see how just completeness, let's write this here. So if I want to graph the expected return of this combination as a function of the weight, I want to put this on my y-axis. I want to put this on my x-axis. And this is a fixed quantity, it's the characteristic of bonds. And this is the premium of equity over bonds, is also constant. So a constant, this constant multiplies this one, which is added to it, so the relationship is linear, just like that scenario. So if you want to graph it, let's kind of look at this. So if you invest only in debt, your weight of equity is 0. And your resulting portfolio is equal to that of bonds. If you invest only in equity, this is going to be your expected return on your overall portfolio. And since you have 2 points, you know that those 2 points are linearly related to, this y variable is linearly related to your x. So if shorting is not allowed, that is just a straight line. So it's the exact same thing that we had here. In fact, the problem is the exact same. It's just the weighted average of the returns. Yeah? So this is where you invest only in bonds. And here is where you invest all in equity. And then anywhere in between. Yeah? Questions? So, for the relationship between asset allocation, so weights, and expected return, nothing changes across those 2 different settings. Whether you're investing in risky assets or risky and risk-free, the return of the portfolios is still going to be a linear relationship with the weight of the assets. Things get weird when we deal with risk. What about the relationship between the risk of P and the weight of equity and that? So recall that the risk of a portfolio is equal to the weight of the first asset, risk of the first asset squared, plus the weight of the second, risk of the second squared, plus twice the weight of the first, risk of the first, weight of the second, risk of the second, correlation between first and second. And then you take the square root. So this is definitely not a linear relationship in terms of weight. In fact, there are squares, there is a square root in the middle of it, and then there is this guy here. What is that?
That's how correlated the.
Is the correlation between those 2 assets, right? So how those assets behave relative to each other. And this correlation takes values that range between -1 and +1. Yeah? So if the correlation is +1, that means X and Y move together always in a proportional way. If the correlation is -1, that means X and Y move in opposite direction, always in a proportional way. So it could be a 1-to-1, it could be a 1-to-0.5, or whatever, but it's always like that. What about if correlation is 0?
No relation between the two.
So if correlation is 0, it appears that the two are not dependent with one another, even though what I just said is not quite correct. So what affects the risk of the portfolio is not only how you mix the two assets together, but also how those two assets relate to each other. And even though a correlation takes a value between -1 and +1, there is an infinite number of values that it can take within that interval. So how can we make sense of this? I would say let's start with this extreme. Let's assume a value for correlation, see if we can make sense of these. And if we can make sense of it, then let's pick another value correlation that is manageable, see if it makes sense, and maybe we can relate the two extremes. So what happens when the correlation is +1, what happens when the correlation is -1? And maybe we can generalize and get an idea of what could happen if the correlation is a number between the two, okay? So, let's take case 1, and we fix correlation between equity and debt to be +1. So those two assets move together all the time in a proportional way. And let's see what happens to the relationship between the risk of P and the weight of one of the two. And now we're assuming that those two assets behave in a specific way. So the way we calculate the risk of the portfolio is like that. So you have weight of equity, risk of equity, square plus weight of debt, risk of debt, square plus twice weight of equity, risk of equity, weight of debt, risk of debt. What happened to correlation?
Increase the risk overall,
No, what happened to correlation in here? Why is it not there?
because it's just one.
Because you said it's 1, right? So correlation is 1. I didn't write it, you're just multiplying by 1. So let's see if I can make sense of this algebraic structure here. Let these be equal to A, and WD sigma D, I'm gonna call it B. Okay? I'm so hungry now, my stomach is growling. Can I rewrite this in a different way, just substituting, and so that it looks less intimidating? This is just A, by definition, squared. This is what I call B, and it's squared. This is A again, this is B. And I get that. Remember the square of a binomial? How could you forget a square of a binomial? Of course you remember it. So if you take A plus B,
Oh, that is just straight up then.
and you square it,
Mm-hmm.
you get so apply the distributive property, this times that, this times this, you get A squared plus AB, then multiply B times those guys, you get AB plus B squared, which is, if you arrange it and combine terms, you get that. So it means you can write this guy as A plus b squared, and you're taking the square root, it just gives you the inside of the root. Yeah, you're taking the square root of something that is squared. So this means that this whole thing can be written as root of equity, risk of equity, plus weight of that, risk of that squared, square rooted, which is weight of equity, risk of equity plus weight of that, risk of that. So it's the same structure as this one. So when you're taking the square root of these, it simplifies to just that. And not only that, but I call that WD can be written as 1 minus WE. Replace stuff around and you get sigma B is equal to sigma E WE plus 1 minus WE sigma D. And distributive property, rearrange terms. You've seen this structure before. This is just sigma D plus WE sigma E minus sigma D. So what was I trying to accomplish? I wanted to show a relationship between what? Between risk and weight. So I want this to be my y-axis. I want this to be my x-axis. This is a constant. This is a constant. So how does the relationship look like? So if you're dealing with two risky assets, oh, this is not y, this is WE now. If I'm dealing with two risky assets, and I invest only in, if the weight of equity is 0, means I'm investing only in bonds. So this is my sigma D. If I invest only in equity, this is my sigma E. So I'm investing only in bonds here, I'm investing only in equity here. And what is this relationship saying? If I mix the weights, those 2 points are connected by what? By just a line. So this is the equation of a line. So if you know the two endpoints, you get that. So risk in this case is just a linear function of weight. Questions? So this only works if correlation is exactly 1. So I'm dealing with two assets that behave in the exact same way all the time, or at least in a proportional way all the time. Questions? So let's try the next case. Let's pick correlation equal to 0.
Huh?
You good?
You don't want the relationship between weight of equity and risk of P if correlation between equity and that 0. So we're going to use the exact same formula from before. So we have sigma B is equal to weight of equity, risk of equity squared plus weight of debt, risk of debt squared twice weight of equity, risk of equity, weight of debt, risk of debt. But now we're multiplying that by what? Correlation is 0, right? Yep. So what happened to this thing? Becomes that. Do you agree with that? I have no idea how to graph it. I've never seen something like that. But I know that if you consider case one, I recall that if correlation between DNA is one, this thing was like that. So holding everything else the same, which quantity is larger? This one or that one? Well, using the exact same values for weights, holding the weights constantly, assuming that we're dealing with the exact same two assets, this is always going to be larger than the one before, right? Of course, except at the endpoints. At the endpoints, except at, if the weight of equity is 0, then in both cases, sigma p is equal to sigma d, and the weight of that, sorry, weight of equity of 1, yeah, the sigma p is equal to sigma d. So if you exclude those endpoints, this is always going to be less than that. So let's graph these. Let's see how this could be graphed, knowing this fact right here. So this is my weight of equity. This is my sigma p. This was the case where correlation was 1. And so if correlation is 0, we know that if weight is 0, we are here in both cases. If weight of E is 1, we're here in both cases. How can I start from here and get here, but at the same time always be below this one? And clearly you don't get jumps, right? This is not an equation that has jumps in it. We don't even know how to draw those. So the only way to draw it is if you start here, immediately you're below this thing. This is something that looks like that. It's always below and it's continuous. Yeah, you never jump with a pencil as you draw it. So I don't know exactly if it's gonna be this low. It could be like that, I'm not sure, no clue. But I know that it's not gonna be it's not gonna be overlapping this, it's not going to intersect it, I know it's not gonna be above it. So while I cannot draw it perfectly, I know that it's tendentially below that. Does it make sense? Yeah. So when you mix into assets with a correlation of 0, if you increase the weight by a certain amount, you're not increasing the risk by a proportional amount. Like in this scenario, if you increase the weight, focus on this curve right here. If I increase the weight by this much, risk hasn't changed that much in the two assets. But if I change the weight from here to here by the same quantity, risk has increased by this much. If I'm here, increasing the weight by the same amount, increases risk by a huge amount. So this is making things quite interesting because I could increase